All right, hi everybody. We're going to continue our work in chapter 5. So if you could please open up your notes, we are going to get right into it. We're going to start off today talking about a perpendicular bisector. This is a term that we have used before, but we have not defined. So let me get perpendicular bisector up here. All right, let's start with a picture. So if we're going to have a perpendicular bisector, what we'll be bisecting, we know we need to have a segment because bisect means we're going to intersect at the midpoint. So I'm going to take a point. I'm going to put it right there. Let me grab this. All right, so bisector means we are going to intersect at the midpoint. So I'm going to mark this congruent to that. So that's our bisector part. Of course, our perpendicular part means we need to be intersecting to form a right angle. So let me draw a line. Could be a segment, could be a ray, could be many things. It does not have to be a segment like our blue segment there. There we go. So segment bisector. We are going to say a line is a segment bisector if and only if it intersects at the midpoint and is perpendicular to the given segment. Perpendicular. Let's fix that. Okay, a line is a perpendicular bisector if and only if it intersects the segment at its midpoint and is perpendicular to the segment. All right, there we go. Now just keep in mind, if you haven't watched the video before of mine, that you can always pause the video if you need to quickly finish writing something down. I'm going to keep going. So let's take a look at perpendicular bisectors a little bit. And to explore, we're going to go to our friend GeoGebra. I am going to create a segment. I am going to construct a perpendicular bisector. So under my construct tools, we'll see that third one looks like a perpendicular bisector. And when I hold my cursor over it, of course, it is a perpendicular bisector. So I'm going to come over here. I'm going to choose that. So there's my perpendicular bisector. Now what I'm interested in doing is putting a point on that perpendicular bisector. Now I've done that. I've got this point C. Notice I can move it up and down on the perpendicular bisector. Now what I want to do is I want to measure the distance between that point on the perpendicular bisector and each endpoint of the segment. And right there, first one off, what do we notice here? We notice that the distance from C to A equals the distance from C to B. That C is what we would say is equidistant from A to B. Is that true as I slide this up and down? Yes, it is. And I think that's pretty intuitive. I think that you guys would have guessed that even before I got on GeoGebra. And we will notice as we slide down here, that is called our perpendicular bisector theorem. It states that in a plane, if a point is on the I'm having pen issues with my Mobi here, guys. Sorry. Might have to type a lot of things in this video if this continues. If it is on the perpendicular bisector, of a segment, then it is equidistant from the endpoints. Of the segment. All right, so when we look at point C in this diagram, notice it's on the perpendicular bisector. How do I know CP is a perpendicular bisector? Well, I see that P is the midpoint of AB. I see those congruent marks there and there, and I see the perpendicular sign for the right angle right there. So C is on the perpendicular bisector. So what we know from this is that CA equals CB. All right, I just switched out Mobi's here. Let's see if this is better. So I know, there we go, CA equals CB. Now notice I did not put a segment sign above these, and I did not use the congruent sign. The perpendicular bisector theorem says the word equidistant. So that word equidistant tells us we're talking about distance, which is our numbers, and that's what we have. So you should be asking yourself, just like we do every day in this class, how could I prove that this is true? How do we know that the point has to be equidistant from the endpoints? How are we going to prove that? This is a theorem. We can prove it. So when I look at this diagram, I can see my givens that CP is a perpendicular bisector. That's the if part. The then part is what we want to prove. So I want to prove CA equals CB. Now hopefully, as you picked up in our first lesson here as we started chapter 5, is that if I want to prove something, I know my strength in proving things comes from proving triangles are congruent. And you should have already noticed when you look at this diagram that we have two triangles. So you should be asking yourself, do we know that those two triangles are congruent? And the answer to that, of course, is yes. So, 1, what's our given? CP is the, can I use the, are you guys okay if I use the perpendicular sign to abbreviate? The perpendicular bisector of AB. Given. So what does it mean to be the perpendicular bisector? We just wrote that definition right at the beginning of this video. Okay? It's a perpendicular bisector if and only if it intersects a segment at its midpoint and is perpendicular to the segment. So if it's a perpendicular bisector, we know P is the midpoint of AB. And what else do we know? CP is perpendicular to AB. Those are both off the definition of perpendicular bisector. All right, now before we write anything down, let's think this through. Let's come up with a plan. Let's talk it out. Let's see here. If P is the midpoint, I know those are congruent. If it's perpendicular, I've got a right angle here. I would also have a right angle there. And those are congruent. As I look at the triangle on the left and the triangle on the right, we should also spot the reflexive property. We're going to say that these two triangles are congruent by what? Side angle side, right? So we've got side angle side, and if those triangles are congruent, we're going to be able to work with CA and CB. All right, so how do we get there? Let's write out each step. P was the midpoint. That means AP is congruent to BP. Definition of midpoint. We know that definition of perpendicular, actually we want both of those to be right angles. So instead of using the definition of perpendicular, we had a theorem that said if two lines are perpendicular, then they intersect to form 4 right angles. So I'm going to say angle APC and angle BPC are right angles. Now, what theorem was that again? Theorem something. 3 point what? Well, honestly, I don't remember that number off the top of my head. I'm going to have to go into my notes here. Let's see if I can do this. Let's see. Let's get to our notes. Let's go back to chapter 3. Scooting down. Where is it? Right there, theorem 3.9. If two lines are perpendicular, then they intersect to form 4 right angles. That's what we needed. We needed theorem 3.9, didn't we? Now, if we're going to use side angle side, we don't just say that those are right angles. We say that those angles are congruent. So our next step is to say angle APC is congruent to angle BPC. What tells us all right angles are congruent? Slide my picture. Let's go to the top of the screen. Hi, everybody. That is the right angles congruence theorem. All right, so we've got, sorry if the video's been glitchy here for the last few seconds. I've had several interruptions. We're fine though. All right, where am I at? Let's see here. I've got those sides congruent by the definition of midpoint. We have the right angles. We've got the right angles being congruent. We're to the reflexive property, aren't we? CP is congruent to CP. Let's see here, what step am I on? I'm on step 6. CP is congruent to CP by the reflexive property of congruency. There we go. All right, so now, boom, we've got side angle side, don't we? Triangle APC.
Would the following students come to the office? Dylan Carty
is congruent to triangle BPC, and that was by side angle side. Now, what are we trying to prove? We're not just trying to prove the triangles are congruent. We're trying to prove this perpendicular bisector theorem, which tells us CA equals CB. Well, if the triangles are congruent, we know their corresponding parts are congruent. Segment CA is congruent to segment CB. By the definition of congruent figures.
Andy Hayes, report to the office.
Now, the word was, again, equidistant, that CA equals CB. If those segments are congruent, we know their lengths are equal. It's been a while since we've had to do this step in a proof. If two segments are congruent, then their lengths are equal. That is the definition of congruent segments. And there's our proof. We just did it. We proved the perpendicular bisector theorem. We prove that if we have a point on a perpendicular bisector, that it is equidistant from the endpoints of the segment. All right, so now that we have that proved, of course, we can feel better about ourselves. We don't want to just accept things to be true. I proved that. I feel great. I know I can move forward, and I can use my perpendicular bisector theorem. So let's see how that we can do that. Let's look at example 6. AC is the perpendicular bisector of segment BD. Find AD. Well, AC is the perpendicular bisector. Boom, boom, of BD. I want to know how long AD is. Well, A is on the perpendicular bisector, and we just said if a point's on the perpendicular bisector, it's equidistant from the endpoints. This is congruent to that, isn't it? So 7x minus 6 has to equal 4x. We can solve that, subtract our 7x, divide by -3, x is 2. Now I haven't completed this problem. I wanted to find the length of AD. Well, if x is 2, AD is 4 times 2, which is 8. Got it. Now, here's the beautiful thing about this theorem, and you're going to find out this is true a lot in this chapter. If you forget the perpendicular bisector theorem, pretty soon we're going to look at an angle bisector theorem. We're going to look at lots of different theorems this chapter. Even if you forget them, you should always just be able to ask yourself, are the triangles congruent? So if you forget the theorem, and I looked at this, I want to find x, okay. Well, perpendicular bisector, well, we've got that, we've got the reflexive, okay, it is side angle side, yes, those have to be congruent. All right. So now, hey, we saw this in our lesson yesterday. Here comes the converse. Okay, take our if then and switch it. Originally, we said if it's on the perpendicular bisector, then it's equidistant from the endpoints. Converse that, flip it. If it's equidistant from the endpoints, then it's on the converse, right? Or on the converse. It's on the perpendicular bisector. Okay, let's take a look in GeoGebra at this one. So let me go and delete this perpendicular bisector. Boom, it's gone. I'm going to take a point. I'm just going to put it up here, just hanging out somewhere. Now I'm going to measure the distance between C and A and C and B. Is it equidistant right now? No, it's not. But let's see if I can find a spot where those numbers are the same. Oh, getting close. Boom. They're the same. Okay. So where do you think this point C is? Here's my perpendicular bisector tool. Right on the perpendicular bisector. All right, so let's fill this in. In a plane, if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. Now, of course, you should be asking yourself, how might I prove this? I think that might be important to be able to do. All right. Oh, there it is. Prove the converse of the perpendicular bisector theorem. Here's what I want you to do. I want you to pause the video. Might help to listen to directions first, right? Okay, so when I'm done giving directions, you're going to pause the video. You are going to then try to complete the proof of this converse. When you're done with the video paused, I want you to hit to play the video, and then magically my proof is going to show up. So, pause. All right, we're back. So, just to clarify some things, we're going to prove that D is on the perpendicular bisector. I have to prove PD is the perpendicular bisector if this were to keep going. So, ready for this? 3, 2, 1, boom. Okay. Here we go. So, I started with my given that D was equidistant from A and B. So, my given is AD equals DB. Now, I know if they are equidistant, if they're the same length, those segments are congruent by the definition of congruent segments. Now, I had to connect P to D. What gives me the authority to do that? Is that legal? Well, as long as I define what it is, like we talked about in class, I can draw on this auxiliary line. So I define PD to be the perpendicular line from D through AB. There has to be one. That's the perpendicular postulate. So I stated that my other given was PD is perpendicular to AB. Well, now can I prove these triangles are congruent? Well, I've got those congruent. I've got perpendicular right angle there, right angle there. I have the reflexive property. These triangles are going to be congruent by hypotenuse leg. Let's walk through the steps there. If I know I'm going to use hypotenuse leg, I have to say the right triangles. So perpendicular gives me the two right angles by theorem 3.9. We already used that one this lesson. If they're both right angles, both triangles are right triangles. That's the definition of right triangles. I've got my reflexive property. PD is congruent to PD. That gives my triangles congruent by hypotenuse leg. Now my goal, I'll come back to that, don't panic. My goal is to say that PD is the perpendicular bisector. We've got the perpendicular part. We need to make it a bisector, don't we? So to make it a bisector, we have to show AP is congruent to BP. We've got the perpendicular part of perpendicular bisector. We need the bisector. We need that congruent to this. So I said if the triangles are congruent, AP is congruent to BP. This must be congruent to that. Now, that makes PD a perpendicular bisector. We already had the perpendicular part. Now we have the bisect by the perpendicular definition of perpendicular bisector. Questions there? Good. I knew you guys were quick learners. All right, now let's use that here. To help us in example 8. Find GH. Find G to H. Well, notice this point F. What do we notice about it? It's equidistant from G and H. So this perpendicular bisector has to keep going through the point F. If a point is on the perpendicular bisector, it's equidistant from the endpoints. If it's equidistant from the endpoints, it's on the perpendicular bisector. What's true about 2x and x plus 1? They have to be equal, don't they? Okay. Subtract x, x equals 1. Find GH, substitute in. 2 times 1 is 2. 1 plus 1 is 2. GH is 4. All right, so now we're going to explore a little bit more, and I'd like you, let's see, if you can, if it's possible, I'd like you to put this video on one side of your screen, and I'd like you to open GeoGebra with the other side. And we're going to look at something really fun here. So, here it is. I'm going to make a new sketch. Don't save. And if you need to pause it to get caught up, feel free to do that, but I'm going to get started here instead of wasting video space. So what I want you to do is I want you to make a triangle. So I'm going to go to my polygon tool, and I am just going to make a triangle. I don't care if it's acute, right, or obtuse. Any old triangle will do. Now, we're talking about perpendicular bisectors, right? So what I want to do is I want to find the perpendicular bisector of each side of this triangle. So remember, our perpendicular bisector tool is right here. I'm going to choose perpendicular bisector. I'm going to choose this side. Then I'm going to come over here. I'm going to choose this side. Oops, too many clicks. All right, so that's what it looks like right now. I've got the perpendicular bisector of this side right here and the perpendicular bisector right there. Now I'm going to make the perpendicular bisector of the third side. There it is. Now what happened here? These three perpendicular bisectors intersected at one point, right there. Now, whenever three or more lines intersect, now two lines intersect, that happens all the time. But whenever three or more lines intersect, we call that a point of concurrency. So you hear that word concur, concurrency. Concur means to agree. I don't know if you've ever, watched the doctor show, and a doctor might say, "Do you concur?" He's saying, "Do you agree?" A point of concurrency is a point where these three lines all agree. They all agree on that point right there. That's a point of concurrency. Now, you might want to hang on to your socks because I'm going to knock your socks off right here. Do you agree that every point on this perpendicular bisector is equidistant from those two endpoints? And do you agree that every point on this perpendicular bisector is equidistant from those 2 points? And do you agree that every point on this perpendicular bisector is equidistant from those 2 points? So that means this point of concurrency must be equidistant from all 3 of those points. What? Did you hang on to your socks? Did I just knock them off? Okay. Look at that. There's a circle. That this point here is the center of the circle that goes through those 3 points. Now I want you to watch this. Grab a point, grab a vertex of your triangle, move it around. Does that circle always go through those 3 points? Yeah, it does. Now here's what's interesting. This point, it has a special name. It's not just any point of concurrency. It's called the circumcenter because it is the center of the circle that goes through the 3 vertices of the triangle. Circumcenter. Okay. Circle, center, center. It's the center of the circle. Okay. Now watch this circumcenter. Right now it's inside the triangle, isn't it? What happens if I do this? Now it's outside the triangle. So the circumcenter could be inside the triangle, could be outside of the triangle. Okay. Now, right here, boom, the circumcenter is right on a side of that triangle. Now take a look at this triangle. You notice anything about it? Now this is just observation, but it looks like a right triangle. And if you said that, you're right. If it's a right triangle, the circumcenter is on the hypotenuse. In fact, it's the midpoint of the hypotenuse, isn't it? Because that's a perpendicular bisector. It's got to be at the midpoint. So if it's a right triangle, the circumcenter is on the hypotenuse. If the triangle is, what kind of triangle is that? If it's acute, the circumcenter is inside. And if the triangle is obtuse, notice the obtuse angle right there, it's outside. So this point is a special point. It's called the circumcenter. It's the point of concurrency of the 3 perpendicular bisectors. It's the center of the circle that goes through the 3 vertices of the triangle. Isn't that cool? I just think this is one of the neatest things to look at. Look at that. Look at me move it around. Very cool. So let's catch up in our notes here a little bit. Okay. I think we've got some vocab words I talked about. Yes, we do. Point of concurrency and circumcenter. Point of concurrency. The point of intersection of 3 or more lines. Circumcenter. The point of concurrency of the 3 perpendicular bisectors of a triangle. Now, if we slide down in our notes back to our examples and our theorems and all of that stuff, I want you to look right here. There we go. concurrency of the perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So notice, each of these is a perpendicular bisector. I'd like you to mark that. Right angle, midpoint. Right angle, midpoint. Right angle, midpoint. Those three perpendicular bisectors meet at this point P. What is the name of that point? I want you to put a note here. That is the circumcenter. And that circumcenter is the center of the circle that goes through the three vertices. So I want you to sketch the circle that goes through the three vertices. So draw your circle that goes through it just like I drew mine. Now, if it's the center of the circle, we know that the radii of the circle are all congruent, and we're going to use that word equidistant again because we're talking about perpendicular bisectors. So all of these segments that I'm going to make blue, this one, and that one, are all the same length. Very neat. We're going to look at that more in class soon. Last example to finish up our video. Find the missing segment lengths. Now, I didn't put this in there, but we have each of these is a perpendicular bisector of a side. So fill in some missing lengths. If that's 20, this is 20, that's 26, this is 26, that's 22, this is 22. Now notice this distance right here, I'm going to make it a red line, is 26.8. That's the distance from the circumcenter to the vertex. And we know that we can draw a circle, stretch out a little bit more, there it is, that goes through the three vertices. So all of these are the same length. So I want you to fill all in those. Those are all 26.8. Now, this is useful whenever you want to draw a circle through 3 points. And there's some examples, some problems I'm going to have you work on with that. So again, I'm sorry this video got chopped up a lot. I had a lot of interruptions, but I think we looked at some pretty cool things. Thanks for tuning in. We'll see you next time.